assumption is, I think it's important content we should remember these three assumptions. The first one is elastic assumption. Still, the concrete are elastic material. Actually, that's not true. No, especially for the concrete, it's not elastic material. And the plane section assumption. This assumption B is also very important assumption. We will use it often in the real project. We use this plane section assumption. Cross section means detail of the deformation. That means this section will no swap or something like this deformation to keep the plane. Ignoring tensile ability of the concrete. That's the three basic assumptions for this method. So for this figure is the distribution of the stress for this rectangular section of the reinforcement concrete. In this method, the rubber stress method, under the following assumption, we can draw the distribution of the stress like this straight triangle. But the real situation actually is not this. Because in this method we use this elastic assumption, so that means the concrete still receives the elastic material, then the strain and stress, the relation is a straight line. But actually, the concrete is a plastic material, it's not elastic. So in the real situation, the distribution of the stress or strain is not like this. It should be a curve like this. But in this method, we make a simplified. We just draw a straight line because we use this assumption. So this method is making the calculation is easy, but it's not so precise. So that's some of the characteristics of this method. The safety factor K is greater than 1. If this safety factor K is smaller than 1, that means your design is not safety. So just now we said the safety K, the K here should be larger than 1, and the value large will got more conservative results. The higher value will have a higher safety potential, however, resulting in more material. So they make it design too conservative. So let's say you use maybe some of the material is not necessary. Just waste the material actually. There's no consideration of the diversity of the structure, because like the bridge of this building, there's lots of components, the column, the beam, or other components. So, but in this method, we just use the simple formula, the stress smaller than this value. They didn't consider, because in this structure, different position, the load level or the stress level is different. If you use the same checking level to design it, so that means maybe some place is okay, but some place maybe is too conservative. So in this method, there's no condition of the diversity of structure. Actually, in the real design, you should consider different components. You use different methods to design. For the beam, for the column, for the pile or abutment, of course it's different. The force, the stress level is different. You cannot use just one formula to design all the components, all the structure. So this method is easy, but there is no consideration of the diversity of the structure. For structure, on the one hand, it's needed to consider the loading carrier capacity, and on the other hand, it's needed to consider the serviceability. So that's what's the mean. Load carrier capacity and the serviceability, that's different situation. Loading carrier capacity means this structure, how large load this structure can bear or resist.
Stress. Not resist stress or force.
Yeah, the force of the load. But for the serviceability, that means, and maybe how wide the crack, or how large the deformation, or the stress level. Once the deformation is larger than somewhere, the structure cannot be used. But the structure will not collapse or destroy. It just cannot be normal use. So that's a different level. Of course, for this level is I think the stress level is smaller than this load carrying capacity level.
This one is what I'm not telling.
So
Serviceability.
yeah, this serviceability is for the normal use. Because for the normal use, you should keep suppose the bridge, you keep this horizontal level. You cannot have got a large deformation, or in the beam you cannot get a very large, very wide crack. But once this crack, you reach this maybe 1 centimeter wide, or of course in the real situation maybe 2 millimeter wide, something like this. According to code, maybe the serviceability is not suitable or not okay. But for the loading carrier capacity, it is still okay. The bridge will not collapse. So this level is maybe a very strict level. This level, something maybe the second level. We can divide it this first level, the second level. For if just see the stress, the stress level for this is higher than this one, is larger than this. Actually, for this loading carrier capacity, I think is related to the safety of the structure, and the serviceability actually is related to the durability of the structure. So for this point, yes, or okay. So see, safety factor K is determined on empirical judgment, not a scientific basis. So this value, as just now I said, it's not a scientific result. It just got from the experience. So that means this method is not so
Precise.
yeah. But for some situation, for this large wall structure like the dam or this very special shell structure, it's very hard to get the theory formula to use. In this situation, this method is suitable. So just make all this every component is under the smaller than the design level. So let's keep this for safety. But maybe you waste on material, maybe it's too conservative, but use a simple formula to calculate it.
But I'm sure the formula, you said the design strength is strength of materials over factor of strength. But so if the factor of safety is higher, the strength of the materials is lower.
Strength of material is actually you can see the strength of the material actually is the value of the fixed value. Or if you design, if you select one material, maybe you select C50 concrete or some HRB 335 reinforcement. Once you have determined what type of material you use, so this value actually is fixed. So the value of the factor of safety, larger this value, that means you need a lot of the material, more material. Or in another way, if this value of safety factor is larger, then if you keep this design stress at the same level, then you can improve the material strength, then reduce the amount of the material. So maybe when the K is 1.5, you use 100 ton C50. If your K equal to 2, maybe you can use maybe 80 ton C60. You can go to the same level, design level. Is it like this? So when the key changes from 1.5 to 2, if you still use C50, that means maybe you need to 100 or 130 something like this. So the second method, factor phase of the design method. Actually, this method is a little more than or is developed from the first method. This method is developed in 1930s. For this, so cross-section internal force reaches a certain limit internal force and external loading and commuter field. So for this design method, taking flexion member as an example, expressed like this, where F is the commuted moment for the section, MU is the outward movement, then the cross-section bear, and the K is the safety factor. So this method is determined by the cross-section internal force. Once the cross-section internal force reaches a certain limit, then we can call this component field or damage. That means we need to, in this method, we need to restrict or when we design, we need to make the cross-section internal force smaller than some value to avoid the field of this component. You see, in this level stress method, we use sigma stress. And in this second method, we use the moment. You see, moment share is a force. Stress actually is a, what's the difference between force and the stress? Force and the stress.
The stress is like the impact.
Stress is due to the nature. Force is what
On the load, like the impact on the load.
Actually, the unit is different. The unit of the force for the shear force may be
the direction.
Newton or
Newton.
Newton
The unit.
plus a meter.
Newton per meter.
And for the stress,
Joule.
what's the unit of stress?
Force. Okay.
Ha.
Pascal.
Pi.
Pascal.
Yeah. So what's
Pascal.
yes? So actually, it's the
So
it's
like
the
pressure.
yeah.
Okay.
Since then, like this, stress, what's the real formulation stress?
Force by area.
Force by
Force by divided by the area.
area.
We check the real.
Done by the square root.
Here is pound. So in this different method, the second method we use with the design level actually is the moment or force, the internal force, not stress. So that's the difference. The first level stress, and the second is they use the internal force to determine the design. So for this second method, the assumption, the failure phase for the component is taken as a base for the calculation. Without regard to the tension of the component, this assumed with the first method, the first one method. And the distribution of the component stress in the compression zone is a curve, and use the equivalent rectangular stress block for calculation. Okay, like this. We use this rectangular section to replace the real curve distribution when calculating the compression force. Equivalent rectangular stress block. The real distribution of the compression stress actually is a curve, but when we calculate, we use the equivalent rectangular. This equivalent rectangular to calculation this. And for this method, we got these characteristics. This method considers the force usage of the material, plasticity and strength, and the ultimate load is confirmed by the experimental test. What you call x to this value is equal to h sigma z. If batch is smaller, that means this distance is smaller, so the area of this part become larger. See, that if the batch is smaller, that means this vertical x move this way. shadow become larger. This area represents the activity of, because this value z smaller than 0. That means this becomes larger. That means this structure becomes more unreliable. The reliable probability gets smaller. So once the value of beta getting larger, that means the vertical axis move this way. Move this way, that means this area becomes smaller. This smaller than 0, getting smaller, that means the structure becomes more stable, more reliability. So that's why the value of beta is greater or larger is better. Larger value of beta means you have a high guarantee for the probability. It's just from this figure you can see. Once with the increase of the value of the beta, the figure moves this way, or you can see the vertical axis move this way. The area of the center is getting smaller. This area represents the unstable situation. Z equals 0 means the limit state. Z larger than 0 means the stable situation. When we design, we make sure this Z larger than 0 as more as large as more as possible. So we can make this beta, the value beta as large as possible. So understand this the meaning of this figure?
Yes.
So the target reliability index is used as a reliability index for basis for truck design, and it is defined by calibration method or engineering, so linear and equal optimization. Calibration method uses the reliability calculation method based on the static parameters for the basic variable and the probability distribution type, and the reliability index implied on the past, taking it as a base for the design target index. So in the code, we got this table. Since level 1, 2, 3, and the damage type, how failure, brittle failure. You see, brittle failure means is breaking suddenly. So for this region, we need to have higher reliability index because it's so dangerous. For this ductile failure, that means the plastic failure, you have time to prepare to repair this. So compared with this failure, the index is smaller, a little bit smaller. So that means the failure of this type is more dangerous. We should have higher reliability index. Maybe for this brittle failure, we need to keep it 99% guarantee. Or for this, we can make it relax to 95 or 94, something like this. It's a little bit smaller. Because this failure, once this happened, it's just a disaster. It can be no time to repair, no time to. But for this failure, you have sometimes you have a chance to repair to just to save it.
With this dictator where we can do patterns like you can come maintenance mechanics and lessons.
Yeah, because for this type of failure is the failure, the deformation is development gradually. It's not suddenly. You can most time you can see it. You can know it's going to or maybe it's going to the large deformation, and if this keep on going, it's going to collapse. But for this situation, for this failure, maybe at the beginning, maybe you don't know what's happening, suddenly happening. So for this situation, it's more dangerous. The requirement is more strict. And for the sixth level, first level is more strict. That means your structure is very important. And two level, second, third level, that means your structure is important, but it's not so important. And this another level means the structure is just normal structure, maybe not so important. Suppose this structure, like the building in the university, lots of students in the building. If this building failure, maybe lots of people will die or hurt. But if suppose the structure is a very small house, or maybe just just in your own home, something for not a live, maybe just put something inside. What's the name? I forget this word. Warehouse or this storehouse, warehouse. Even this structure collapse, maybe the loss is limited, not so much. So that means it's not so important. So normally it's belongs to level 3. So level 1 is the most important. Level 2 is important. Level 3 is just normal. It's not so important. So the index is smaller. So that's the different safety level and different damage type. So the index, reliability index, the value is different. Altogether, large value means the requirement is strict, and the reliability is high. So you know this index, reliability index, better. Normally we use this value. See now, here is a value, not the probability. Normally we see the 95% guarantee. 95% is a guarantee, is the probability. But here is the index, it's just a change. How change? Just use this. Actually, one of this value or match is referred to maybe 95% or 99%, something like this. It has a relation 1 to 1 to 1 to 3. So 15 minutes. I have 15 minutes left. On this figure, okay, a little bit. And the transit state. Transit state is when the bridge carrying temperature during construction. The condition corresponding to the bridge construction phase and consider ultimate limit state. So this difference for the persistent state, you need to consider not only ultimate limit state, also serviceability limit state. For this constant state, you need to consider ultimate limit state. Because during the construction, of course, you have not open to use. You do need to consider the serviceability limit state. The third state is existential state. This is the accidental situation during bridge service. This is corresponding to the earthquake situation, the short of bridge, short of the shape, something like this, and consider also ultimate limit state. So these two transit and accidental this state both consider the ultimate limit state. Only this persistent state you need to consider not only ultimate limit but also serviceability limit state. So this here is a little bit complicated. This design condition. For the spread design, you need to consider this will be persistent state and
Transient state. SI. No.
And another one is the exit.
Accidental state.
These three for the structure design, you need to consider these three states. During this three states, compared with this, we also got two limit states. Ultimate and serviceability. move. Like just use RT. RT and the service. So for the persistence, this persistence state, both of these limited states you need to consider. But for this two situation, only this ultimate state you need to consider. So aside this thing,
Yes.
these three means the different working situation. This one is the phase of the construction open to use. This for just the construction stage. This one is for the exponential load, maybe a speaker and a very short time situation. Different working situation, working stage regarding to different limit states. Limit state related to the force or to the design level you need to consider. So this is three state and 20 meter states. What's the relation between this? I wish you can remember. The bridge and the cover structure damage according to the severity of the consequence can divide into level 1, 2, 3. Actually we have introduced before. Level 1 means very serious. Level 2 is serious. Level 3 is not serious, it's normal situation. So for the loss library, important loss library, of course, it's very important, very serious. If it's damaged, the consequence is very serious. So because of the important coefficients, gamma 0, the value is 1.1. For the second level, for the middle library, something important is small gradient. This level, the coefficient gamma 0 is 1.0. For some grade is not a normal small grade or cover, it's not serious. This gamma 0, this coefficient, just take it 0.9. So different level of this gamma 0 to keep the value. So what's the use of this important coefficient? What's the use of this value?
I think we use it in one form.
We use it in one form. Is this formula? This one? Yeah. So that means for normal design, maybe this value is 1, just 1.0. If the structure is very important, that means improve the standard level 10% or make this structure stronger or more reliability. So this is the expression of the limit state design. Ultimate limit state is established based on the domestic theory. And the design principle is that design value of most maximum combination of the action is also called the basic combination, must be less than or equal to the design value of structure resistance. The basic theory. expression of the ultimate unit state is like this. Gamma 0 is the important coefficient for structure. SD is the effect induced by the load. R is the resist. So that means the resist of the structure must be larger than the effect induced by the load, multiplied by the gamma 0. So in this formula, SD is the design value of the most maximum combination of the action. You can see SD is the combination of action, not only one or two action. Maybe there's several different types of action as the combination together. Maybe the self-weight, the vehicle, the passenger, or the wind, or the water force, many different force. But it's not a 1 plus 1 plus 1 plus 1. Different roles or different coefficients. Or use this to watch the video.
Let's just continue.
And gamma 0 is the important factor. We have introduced the 1.0, 1.1, 0.9, something like this. Corresponding to the structure safety level 1 to 3. And the FD is the design value experience of the material. AD is the design value of the geometrical parameters. This value actually is you can just check on the code. It's it's a geometrical parameters. When there is no readable date, AD mistake. The standard value of the geometrical parameter is namely specified value in the design document. Just look at the code and you can find this value. So design principles for the persistent state is serviceability limit state. So this serviceability limit state, this one is for the hunting limit state. If the limit state, the formula is different. Say for the serviceability limit state, the formula is like this. It's more simple. It's S smaller than C1 hours. This limit is based on the elastic theory or plastic elastic theory. And use short-term action combination and the long-term action combination, or short-term action combination considering the impact of the long-term action. And the crack capacity, grade 1 cell deflection. So for the serviceability, merely check this crack capacity, crack 1 deformation. The calculated value should not be more than the prescribed value in the code. The expression is so simple, just smaller than this. So the one for the one C, what does it mean C? C is the limit value for the component reaching normal use, such as deformation, crack loss, or cross-section stress, something like this. S is also the convenient design value of the certain limit. So here, the most important thing is this: S, the effect induced load. S is not just one value; it's a different load combination together. But the combination is not just 1 plus 1 plus 1. Different load have different the component factor or different coefficients. It's not one, maybe 1.4, 1.8 or something like this. According to the situation. But different situation you can check the code, you can find which coefficient you should use. But you should know it's not 1 plus 1 plus 1 plus 1.
Okay.
Design principle of the stress expression of the persistence and the transient condition are very complex, and different components have different design principles. For the transient, for reinforced concrete and pre-stressed concrete member, stress induced by self-weight and construction load in fabrication, transportation, and installation stage based on the transient condition, not exceed the limit. And for the persistence, for design the flexible pre-stressed concrete member based on the persistent condition, stress in surface stage should not exceed the limited value. Also, this slide asked for the limit value not exceed the limit value, but in what situation is different? So to sum up, the structural stress does not exceed the limit values. Design pressing of the limit state design for pressing the transient condition is just the same like this. Where S is the standard value of action, considering the important impact of the recall load factor. The load combination is not considered when loading the company. C is the strike function. It mistake is C to C1, C. So this third part actually is relatively simple. And then we finish this fourth part. Actually, this part, some content I have introduced before. The principle of the value of the material strength, the value of the concrete, and the steel reinforcement. The principle of the value for the material strength. Here, the standard value is a characteristic value of the material strength, which is determined by standard test method according to mathematical statistics using probability distribution by 95% guarantee. Actually, this 0.05 means 95% guarantee. So that means all the standard value of the material strength we got according to with 95% guarantee. Principle for the specified value is to meet the overall strength of the material measured. The special quality should not be less than 95%. This is the expression like this. From this formula, the result you get Fk means have 91% guarantee compared with Fm. Fm is the result of the test every time the test is done. Fk is the standard value. So different time, different experiment maybe have different value. You can very difficult to go to the same result for different tests. But when you do many time tests, the result may be similar, but not the same, but similar. Maybe it's a random result, but which one we use? Finally, we got this formula to get the standard value, 95% guarantee. When Fm is the mean for the material strength and sigma F is the variation coefficient of the strength. The design value of the material strength is then the standard value of the material strength divided by the partial factor of the material performance, like this. So the design value, here the design value have different type. Different material have a different value for gamma. For example, for concrete material, gamma C equal to 1.4745, for steel reinforcement 1.2, for tensile steel 1 strand 1.47. For design value, the compressive stress this is simply wrong. That's the difference. So, for the standard design value of the concrete, actually, we have introduced in the first chapter 1. For the concrete, we got two different values to describe the strength. The cubic compression strength FCU, and also got CK. So this FCU is the result we got by the standard test method, standard specimen, and standard test, standard Q process. Finally, we can got this FCU. All this condition, maybe you still remember. For the test specimen is satellite of the 150 millimeters cube. And standard Q method, temperature 20 minus plus 3 degree relative humidity, or not less than 90% of the moist air, 28 days. Some test method, test lubrication to be coated the surface. The whole process is in pressure. Low speed is this. Then finally we can got this cubic compressive strength FCU. But if we use another actual pressing strength. That means the different specimen size with the 150 millimeter, 150 millimeter, and 300 millimeter pressure. The result is FCK. FCK and FCU got the resolution 0.99 by FCUK. You can got this value between these two different strengths.
So now should XCK go to XCUK. Okay? Very action of conversions. XCUK.
FCUK is the cubic.
Cubic.
FCK is the prism. And for the reinforcement, standard design for the reinforcement. For the reinforcement with the yield platform, you still remember what's the mean the yield platform? It's one yield platform.
Yes.
For the stress sprinkle, for the
Bathroom.
Last
Which one?
for reference
Reinforcement.
to what is in
Yield platform. Oh,
this is the thread and the stress scale of the reinforcement. Once you reach this yield strength, after reach this point, they have a stress process. Normal, if the carbon content increase, this pressure will be shorter, maybe even lost. This yield platform
which video?
means this reinforcement have a very good plasticity, plasticity. Some if the carbon content increase, the strength of the steel or strength of the reinforcement will increase, but the plasticity will decrease, and this yield platform will shorten, even lost. That means this reinforcement will easy to crack. Not crack, maybe once the force increase, the strength will crack. So for the reinforcement of the yield platform, standard value of the tensile strength is taken as standard value of the yield. For no significant yield platform, standard value of the tensile strength of the steel line and stand is taken as 0.85 for the CMB, with graduation not less than 95%. Second B is the ultimate tensile strength specified in the national stand, using a conditional yield strength for design corresponding to the stress reinforcement with the residual strength of 0.2% of the tensile strength. I'm not sure this is in the style or not.
No.
Actually, this is content of the chapter 1, where we introduce the reinforcement, the material, the characteristic of the reinforcement, we have introduced this. If you want to, let's see, we can. Okay. Maybe. Like we didn't use before. So for this figure, this is the stress sprinkle of the reinforcement. Normally, for the reinforcement to have this Earnest platform, we take the value of this point sigma b, this Earnest stress sigma b as the design value strength. But if the reinforcement doesn't have this port, doesn't have this platform, normally we take the value corresponding to this port 0.002 strength. This port, the corresponding strength as the design value, just like this. What is this mean?
Ultimate strength. Ultimate strength.
What?
Ultimate strength.
Yeah. And standard design value of the reinforcement steel strength. In Chinese code CHBC, for the twisted steel reinforcement and the hot rolled steel reinforcement, partial factor of the material performance is 1.2. For the steel stand 1, partial factor for the material property is 1.47. The design value is to pay attention to here. This is two different values: standard value and design value. The design value of the tensile strength of the steel reinforcement is that it's the standard value of the tensile strength divided by the partial factor for this 1.2 or 1.47. Design value of the compressive strength of steel reinforcement is divided by this formula, where ES and EP are the elastic modulus of hot rolled steel reinforcement at steel 1. Because epsilon S or epsilon P, the calculated strength of the similar type. Similar S is equal to 0.002. That should not be greater than the design value of the corresponding tensile strength of steel. So, to me, this just like the sixth factor. The design value maybe we use D, and for the K is the standard strength. FK is we call the standard strength of the reinforcement. FD we call it the design value of the reinforcement. FD equal to FK divided by gamma or this factor. Partial factor if you use gamma. Gamma equal to 1.2 or 1.47. So that means the design value is smaller than the standard value. Sometimes we call H, R, D, this 3. This 3 is the tensile strength standard value of the reinforcement. When you design, we don't use this value. We use this value divided by 1.2 or 1.47 according to your reinforcement, the type. This is the 2.5 part. Okay, we finished the fourth part, and now it's at 12 o'clock.
Okay, I see.
Thank you.
Mm.
Dismiss.